lecture is Lecture 18, and this is going to be a 1-hour lecture because of the seminar this afternoon that's going to start at 3:30. So let's just get started. So this is, we're down here, at actually near the end of the class. So in fact, we're doing extraordinarily well. In fact, today we're going to cover material that the last time I taught this course was offered in Information Theory 2. So you're going to get a taste of Information Theory 2 today. So we're ahead, like I said. So what you should be reading, or what you should have read at this point, is Chapter 8 in the book, which is right there. Okay, this is something you don't have to worry about. There's no new homework. So all you need to do really is sort of concentrate on today's material, and also concentrate on the final exam. So a couple of announcements about the final exam. First of all, so again, my offer still stands with regard to anybody who wishes to not come, well, first of all, to not come to office hours and to set up a special time with me to Skype or Google Hangout or something. If you have any questions, and I'm also quite willing to meet with you over the weekend. Just let's send me an email, we'll set up a time. So if you have any questions, let's do it. There is a final assignment, and the assignment is really nothing except to, in a timely fashion, upload your scanned final exam that we will send to you. So again, everybody will, very soon after you take your final, you will receive back your ungraded final in PDF form by email, and your assignment is to upload it to Canvas. That's all you got to do. It's this. And then lastly, I double-checked in the final exam, and then, there is a typo here. So nothing's ever typo-free. So, maybe this is not. This is, yeah, there is a typo. This should be Wednesday. At the latest, by 4 p.m. You know, if you could do it that evening, as soon as you get it, you can start grading that evening. So, but it's a lot easier. I mean, I'm not going to start grading. We're not going to start grading until we've received all of the finals, because the most consistent way to grade is to grade all problem 1s together, and all problem 2s together, and all problem 2s. It doesn't make sense to grade problem 1, 2, 3, to however many for each exam. So we're not going to start grading until everybody is uploaded. So if you could that evening, maybe next Tuesday evening, upload your final exam, that would be great. So the actual location, this is the exact correct location. So it's next Tuesday, December 10th, at 4:30 to 6:30 p.m. in our original room, Pathfinder. That's where the final will be. So it's a week from today. Okay, so that's it for the logistics. So let's start talking a little bit about differential entropy. Again, so this is a review. The main definition is down here, and when you look at this definition, it's very, very similar to the discrete entropy, except that we use an integral over the support set rather than summation. But other than that, it has the same form. It uses the density function rather than the mass function, and it's an integral rather than a sum, and we only assume that we're only assuming integrating over the positive, the region where the density is non-zero, so not have to worry about logs of zeros and everything. But other than that, it's pretty intuitive once we already have our intuitive notion of the differential entropy. But where it becomes a little bit interesting and tricky was when we actually start looking at the entropy, and we find right away that when we compute the differential entropy of a uniform random variable, then it can be negative. So here's the entropy right there. And we can see that it can be negative or positive. And so what we spent a little bit of time last time talking about was how it makes sense for this to be negative when we interpret this as like a side length of the volume. And we gave an analogy to the discrete case. We also have this property here in the Gaussian case. So this is a univariate Gaussian. So the entropy is exactly equal to 1/2 log of 2 pi e sigma squared. So the sigma squared is the variance of the Gaussian. And so what this is saying is something that, in retrospect, should hopefully be somewhat obvious, which is that the variance of a Gaussian is directly related to the entropy of the Gaussian. In fact, it's modified. It's a deterministic function to map from the entropy to the variance and vice versa. And so therefore, our notion of spread that we have in entropy is like the log, it's like proportional to the log of the variance. So that's a very nice and intuitive result. We also saw that we have an asymptotic equipartition property for the differential entropy, where on the one hand, we see that if we have a stochastic process of IID random variables that each are distributed according to F, which is this stuff here, then if we take the average negative log of the probability, then that converges as n goes to infinity to the entropy by the weak law of large numbers. And then similarly, we define the typical set, which is all events, or it's really the measure of the events that are epsilon close to the entropy in this form. And we saw the typicality theory essentially showed us that basically constitutes all of the probability of energy, just like we saw in the discrete world. So we have that. We also saw a relationship between the differential and the discrete entropy. And the critical sort of intuitive thing to get here is this stuff down here. That we're related by the discrete and the differential entropy, where the discrete entropy is sort of the n-bit quantized version is related by this log of delta, where delta is 1 over n, 1 over to the n. And so we get this right over here. So we talked about that. And I think that's all the old stuff. So that's all the review. So now what we're going to talk about is a little bit more on differential entropy, so the joint entropy. So not surprisingly, like when you have multiple random variables, so far what we've talked about is single random variables. When you have multiple random variables, the joint entropy is defined quite naturally based on the joint distribution of the set of random variables. So here's an example where you have n random variables, and we just take the density function of those n random variables with that vector of length n of random variables, and it's the same thing, just multivariate. Except that in this case we have an argument now, which is a function of the set of random variables. And similarly to how we define the conditional entropy for discrete random vectors, we have a conditional differential entropy for, in this case, it's a pair of two continuous random variables. Now nothing requires x and y to be scalars. X and y could still be vectors. Right? If they're vectors, that's fine. If they're scalars, that's fine as well. But the point is that it's defined exactly analogously. We integrate with respect to the joint. So here's the joint of f of xy of the log of the conditional. Exactly analogous. And that turns out, just by looking at the definition, to be the entropy of xy minus the entropy of x. Sorry, the entropy of xy minus the entropy that you're conditioning on, the entropy of y. That's also unsurprising. Now here's something that we're going to spend a little time on. So we talked about the scalar the entropy, the differential entropy of the scalar Gaussian. So here's a multivariate Gaussian. It's a multivariate Gaussian. X is distributed according to Gaussian with mean mu and covariance matrix sigma, and this is the density function. It's 1 over the determinant of 2 pi sigma, and it's the square root of the determinant, times e to the negative 1/2 x minus d transpose, times the inverse of the covariance matrix times x minus d. So how do we compute the entropy of that? We're going to actually give the entropy, and then we're going to drive it in a minute, but it has a nice form. And it's exactly a generalization of the scalar Gaussian. So there's 1/2 log, there's a 2 pi e, those are the pi and e and a 2 together in the same expression, except that in this case we're raising it to the nth power, which is the dimensionality of the Gaussian. And then rather than the variance, which is sigma squared, we're writing the determinant of the covariance matrix. So the determinant of the covariance matrix acts in some sense like a multivariate spread of the multivariate Gaussian, analogous to how the one-dimensional variance acts as a measure of spread of the scalar Gaussian. This is still an entropy function. we're still measuring concentration or entropy or spread or something. But in this particular case, when you have a multivariate Gaussian, it's measured based on the determinant function, not the which can basically be a positive definite matrix. We have lots of coefficients. And so a couple of things. So it's monotonically related to the determinant. So you've heard before that in some sense the determinant is like the spread or the overall volume or something of a thing. And so this sort of means that if you take the log of the determinant, you get the entropy. So again, entropy is kind of like a log of a volume. And number two, we can actually solve for the determinant of the covariance matrix, and we get something that's proportional to 2 to the entropy. So again, the determinant of the covariance matrix is 2 to the entropy. So we've already said this. The determinant is dense. It's therefore a dense. Is that a word? Dense. Therefore, that's like the combination between therefore and hence. The determinant is therefore hence a form of spread or dispersion. So how do we derive this? I think it's kind of a fun derivation, and it involves some tricks that you see always in the context of deriving multivariate Gaussian quantities. So first of all, we put in the quantity. So this is just the definition of differential entropy. So it's the integral, it's the negative of the integral of f of x. So f of x is the Gaussian. And then we're taking log of f of x. And then when f of x is a Gaussian, log of f of x breaks it into a sum of 2 parts. First, the log, we're computing this in nats, by the way. So the log and the exp cancels out. And so we get what's in the argument. So it's the negative of the Mahalanobis distance between x and the mean. And then we've got this constant out in front, which is log, natural log, in this case, of 2 pi, all this stuff here. That was stuff that was in the denominator. So then when we write this a little bit further, in a little bit other way, so this part is basically the same. And so what we're doing here is we're taking this stuff here and applying it here, and notice that x isn't involved here at all. So the integral over f of x of that stuff, the integral of the f of x part goes away since it integrates to 1 since it's a valid density. So what we're left with is all of this stuff. And the other things we took a 1/2 out. Here what we get in this part is the expected value with respect to Gaussian. So this is just the expected value of the Gaussian is really just the integral of fx of that stuff. And I guess actually officially, you know what, I should since it's an expected value, I should probably have turned, I like to be consistent about this, I should have turned these into capital X's. Those are the random variables. Those are the random variables that are distributed according to the distribution that we're taking expected value with respect to. Right? Everybody with me? So those are capital X's, those are the random variables. And so it's the expected value of a quantity. Now, so we're taking the expected value of this quantity up here. But this is a scalar, right? It's a row vector times a matrix times a column vector that's a scalar. So the scalar is equal to the trace of itself, right? The trace is just the sum of the diagonal entropys of the matrix, and when you have a 1-by-1 matrix, it's just the trace. So now what we're going to do is we're going to use this something called the trace trick. Does anyone know what the trace trick is? It's a really important property of traces. I think I had it a little bit later, but when you have the trace of, say, matrices A, B, and C, these are matrices. What you can write them as is the trace of BCA, which is equal to the trace CAB. So sometimes you can rotate these matrices, and you're just summing the diagonal entries, and the sums of the diagonal entries, the sum of the diagonal entries stays the same under these sort of matrix rotation operators.
So how did you get the trace in the second line, 18.6? Where did the first guy gets a trace?
Well, that's because a trace, so a scalar A is equal to trace of the scalar.
But isn't that an x minus mu a vector?
So this quantity here is a scalar. The quantity that I just outlined in green.
Oh, okay. I think I was reading it wrong. You mean the trace of that whole expression inside the expected value, not just
Yes.
the trace of x minus mu.
Yes, yes. So it's the trace, maybe I should add some parentheses here. So it's the trace of this whole guy. Okay. The trace of everything. And so then that's going to be equal to the trace of all this stuff. And I've just done a matrix rotation, right? I've just moved this guy over to here. And you can verify that about the trace. But we use the trace trick, and it seems like almost any derivation about multivariate Gaussians must somewhere or another use the trace trick. Like for example, for deriving maximum likelihood estimates, or for computing the EM algorithm for mixtures of Gaussians, and you need to use the trace trick, or spend a lot more time on it. But now, as soon as we've got this, we've sort of turned this vector, this matrix, into a constant with respect to what we're taking the expected value of. And so we can take the expected value just of this part here, and the green part, the green constant sort of factors out, and what we're left with is, and then the trace is a linear operator, so we can interchange the trace and the expected value operator, which is also a linear operator. Two linear operators can be interchanged. And so we get the trace of this stuff here.
It's sigma.
Yeah, which is sigma. Exactly. So it's the trace of sigma times sigma inverse, which is just a trace of the identity. And so the trace of identity, of course, is just n, right? So we got n over 2. But now we have two things that we combine together. So we've taken this whole complicated expression up here, all this stuff up here, and we've just turned it down to this n over 2. And then we combine it with the thing on the right by adding a 1, which is log of e. Log of e is just 1, and so therefore we can combine the two things together. And so this is where this e, if this isn't clear, this e here comes from this part over here. It's log of e, and then it's log of e plus log of something else, and so it's log of e plus that something else. And so therefore we get the entropy of Gaussian, of multivariate Gaussian. So here's the trace trick. I should have had that earlier. Okay, any questions about the derivation? Okay, so now we're going to use the entropy of the Gaussian, and it's a very important distribution because, as we're about to see in a couple of slides, the entropy of the Gaussian is the distribution that has maximum entropy amongst all distributions that have sigma as the second moment. That might not make sense, but we'll go through that and we'll prove that in a few minutes. So Gaussians are really important. Like every time you use a Gaussian, in some sense, you're using a maximum entropy distribution. Something that we will prove in a minute. So there's also a Kullback-Leibler divergence, or relative entropy for continuous distributions, and it has a form that I'm sure, at this point, none of you will be surprised about. Talking about surprised, actually, not everybody has signed up for Information Theory 2. So please do sign up. I know, if you want to do me a favor, I'm not going to get a TA unless enough people sign up. So our TA will be out of a job. So he's going to be angry at you if you don't sign up for the class. So that's putting a lot of pressure on you, and a lot of pressure on you. I shouldn't have said that. Hey, rewind. I didn't say
If there's no TA, does that mean there's no homework?
Well, no, I promise you that next quarter there's going to be far less homework. Like there'll probably be 2 or 3 homeworks in the quarter, in all honesty. And I'm actually thinking, I'm debating, I think those who come and sign up can have feedback into whether or not we do a final exam or a project. And so I'm open to doing a final project, which could easily be just a paper reading. Because at that point, by the time we're done with that, you'll be able to read any paper in information theory. So maybe we could do paper, like read a paper from somewhere in the information theory literature over the past 5 years. And that would be the final project. So we can talk about that the first day of class. For those of you who sign up, get a vote. You don't want to do a final. And I think that might be more fun, because it is sort of a more advanced research class. And I think at that point, when you get to sort of more advanced classes, problem sets aren't as critical as they are now, because this is a core class. IT1 is a core class. So sign up. I will even promise, if you're interested, I could continue to do the YouTube lectures, even though it's a bit of extra work, or a bunch of extra work, to be honest. But if you find them useful, I can teach them in the next quarter. So, okay, so, right, so where are we? So, yeah, so don't forget, sign up for the class. Relative entropy for continuous distributions is unsurprisingly this, and it's also, for the same reasons, it's also never, ever negative. And it uses, remember way back at the beginning of the class when we used Jensen's inequality to prove the non-negativity of the column divergence, so we can use Jensen's inequality there as well. And also, moreover, we can get the mutual information quantity for continuous distribution. So unlike the entropy, the mutual information of 2 continuous distributions, which in this case is h of x minus h of x given y, is going to be greater than or equal to 0. So the entropy can be negative, but the mutual information is always going to be non-negative, even in the differential entropy case. And the reason why that is because conditioning will still always reduce entropy. So conditioning reduces entropy even in the differential case. So that means that if you condition on something, it's negative, it's going to get more negative. If you condition on something that's positive, you're going to shrink the volume, effectively. So and if it's the exponent of the volume goes from positive to negative, I mean, again, like we said last time, there's nothing special about 0 when you're talking about volume, it's just an exponent. That happens to correspond when we exponentiate something to a volume length of 1, unit 1. But conditioning still reduces volume. And so mutual information is always non-negative. And again, that comes from Jensen's inequality. Right, so this is what I just said. Conditioning still reduces entropy, which is actually very important. So we still also have chain rules. This is the chain rule of entropy. And we have bounds. So these are some interesting bounds. So the upper bound is something you've probably seen before. So it's basically saying, well, if we pretend like the random variables are all independent, then the entropy of those random variables all being independent is going to be the sum of the entropies of the random variables, and that can only increase the entropy relative to their being measured, taking into account their dependence, which happens here. So that gives us this upper bound. This lower bound, I mean, this is sort of interesting, and it's not typically talked about, but the point is you can still have sort of this additive, summative lower bound. And what you're doing is you're taking the conditional entropy conditioned on everything except for, so the entropy of x of I conditioned on everything except for x of I. And that's a lower bound on entropy. So, but you can get that from a number of ways. Maybe that should be on the final exam or something. Hint, hint. So for discrete entropy, you have monotonicity, namely that whenever you add an item to add a random variable to the entropy is always going to decrease. There's more uncertainty, there's more count. Right? But in so I guess here's a way of saying it, that you can think of, if you think of this, f of a, as a function of the set of the indices of the set of random variables. So a is a set of indices, and f of a is equal to the entropy of the random variables that are indexed by a. And what this is saying is that as a function, as a set function, it's monotone and decreasing. But then when you look at the differential entropy, is it monotone in the same way? And you can see that it's not, simply by just looking at the entropy of the Gaussian, which is basically a log determinant. And the log determinant is not necessarily always going to be increasing, right? Because as we increase the rows and columns of the matrix by, I guess it's really the submatrix, which is indexed by the set A, the log determinant can actually get smaller with more random variables. And the reason for that is you can see this by, for example, as you're adding rows and here's an example. Maybe I should draw a matrix to make this a little bit clearer. So let's say that here's a matrix. I'm going to draw this in yellow up here. So here's a matrix here. And now I've added a bunch of rows and columns to increase the matrix here. If for example, if this entry I, if that bottom entry is very, very small, like much, much smaller than 1, then even if it's the diagonal case or not, I mean, basically what happens is when you take the determinant, we're going to be multiplying that by that guy by, say, a cofactor or something, and that guy can then end up making the whole thing smaller. And another way of looking at it would be, for example, if you think about everything independent, when all of the variables are independent, the determinant is just the product of the diagonal entries. And so if you have, and the diagonal entries are the variances of the Gaussian, and the variance of the Gaussian can be positive, can be greater than 1 or can be less than 1. So when you take the log of the determinant, you're summing the log of the variances, and so you could be adding negative values to your entropy. And so therefore, this is not monotonic already in the Gaussian case, not to mention the arbitrary case. So it's a little weird again. You think, well, how is it possible? Again, when we think of entropy, the discrete entropy, we've gotten this intuition by saying, well, when we have more random variables, there's more uncertainty, there's more information, it's going to be more difficult to compress and all this other stuff. When we have differential entropy, we have we're measuring sort of the log of the volume, but we're also increasing the dimensionality of the space within which the volume is measured. Right? So it's like, does it even make sense to compare? Like, would you rather have, a 3 by 3 2-dimensional grid of something, or a 1 by 1 by 1 3-dimensional cube of something? I mean, those aren't really comparable. When you're talking about a 1-dimensional area versus a 2-dimensional area, or an n-dimensional area is not comparable to an n plus 1-dimensional area. And so it's not really comparable any longer in the differential entropy case, because we're measuring volumes in different dimensional spaces. So if it's going down in value, it's in some sense the units are different. They're not comparable in the same way. That might be one way of getting an intuition. So, I mean, the book actually then goes in and talks a lot about a number of interesting sort of combinatorial and linear algebra results that sort of come right out of the information theoretic inequalities that we already know and love, right? Like, for example, and I'm just going to mention one of them here. This is one of the inequalities that we know and love, which is namely that the joint entropy is always going to be no greater than the sum of the individual entropies, and we achieve equality when all the random variables are independent. Now let's assume that the random variables are jointly Gaussian. Okay, so in which case we know that the entropy is going to be the form of a log determinant. And so once we cancel out common terms, what we're left with is essentially just the determinant part, and we get what's known as Hadamard's inequality, which basically says that the determinant, an upper bound on the determinant of a positive definite matrix is equal to the product of the diagonal integers of the matrix. So if you want a quick and dirty upper bound on the determinant, take a product of the diagonals. And we immediately get this result, which, so I guess in the appendix in the book there were a number of interesting consequences of results that have traditionally not been derived using information theoretic quantities. And maybe these aren't really related so much to information or communication per se, but they're nonetheless useful, and they actually offer some further evidence that information theoretic ways of looking at things is useful for proving and looking at and deriving other results, even if they're not sort of in the core communications area. So I would definitely be aware of that chapter and read through some of the additional ones, because some of them are very interesting and fun mathematical results. So let's talk a little bit about moments and maximum entropy. So with regard to Gaussians, we can actually have a continuous random vector, and we can compute various different moments. And the moments, it basically corresponds in some sense to the expected value of like powers or monomials of certain degrees of subsets of the random variables, and where the degree corresponds to the size of the subset. So a first moment means that it's a monomial of degree 1, which means that you can only compute expected values of individual scalar elements, or the vector expected value, which is just the median. The second moment consists of all of the monomials, all of degree 2, which consists of all pairs. So it includes the diagonal of this matrix, which is the covariance matrix of like the expected value of xi squared, but it also includes all off diagonal things. So this, I think I have a slide for this. So it includes all of these guys. Cij is equal to the expected value of xi, xj. So it's monomials of degree 2. But there are other higher order moments as well, and most distributions have higher order moments. So like a third order moment is the expected value of xi, xj, xk, which is represented by a tensor Cijk. And you've probably heard of skew and kurtosis, which sort of measures, like the mean sort of measures the center of a distribution, the variance measures the spread, and the skew kind of measures. I'm gonna do a very bad job drawing this picture, but it's like, it does it look more like this, or does it look more like this? And the kurtosis, if I remember correctly, is it more like sort of like this, or is it more like this? Something like that. Is it more flat at the top, or is it more peaky at the top? These things, and those are just the scalar high order, third and fourth order moments. When you go to higher and higher order moments, you measure a lot of other interesting properties about a distribution. And in fact, if you measure all of its moments, all infinite moments, you get back the distribution for any distribution. So you can actually characterize a distribution by its collection of moments, which might be infinite in the infinite dimensional space, but still, you can get everything about a distribution through its moments in general. And here are third or fourth order moments. So what we're interested in is like the following. So let's say that Cm is the nth order moment, and let's say it's the tensor. Right. So if it's the first order moment, it's a vector. If it's a second order moment, it's a matrix. Third order moment, it's a three-dimensional tensor, and so on and so forth. Right. So like I said, like any arbitrary complex probability distribution will have lots and lots of high order moments. But the Gaussian, however, is unique in the sense that it has only first order and second order moments, and all higher order moments are zero. So in some sense, like it's not skewed. Like if you think about the sort of scalar moments that we're familiar with, it's not bent to one side or the other side. It's perfectly symmetric. Nor is it flat top or pointy head, which is the kurtosis. Right? It's sort of perfect. Right? the perfect distribution. It's the average. And it doesn't have anything higher as well. And in fact, that's one of the reasons why a Gaussian is characterized, why you can parameterize a Gaussian by its first and second order moments. I mean, lots and lots of distributions have a mean. Lots of distributions have a variance, right? But if you took an arbitrary distribution and computed the mean and the variance, that would only tell you everything about a distribution if that distribution is Gaussian. But if the distribution is non-Gaussian, the mean and the variance don't tell you everything about the distribution. Because other distributions, besides Gaussians, have other moments. With a Gaussian, you say, okay, well, nothing else is going to matter because all the other moments are 0. But still, we can compare distributions. You can say, here's two distributions. They have the same first and second order moments, but they have different higher order moments. In fact, you can compare, well, here's a Gaussian with first and second order moment. And here's another distribution with the same first and second order moments, but with a bunch of other higher order moments. How different do these distributions look or act? How bad is it, for example, to take a distribution that I don't know very much about, compute its mean and variance, and try to say something about it? This happens a lot in data science, right? You say you've got this massive data set or something, and you compute its mean and variance, and you look at it and say, I know something about that distribution now. Because I have its mean and variance, and oftentimes you know very little about it, because it's not Gaussian. But the question we want to address here is amongst all distributions with the same first and second order moments, what distribution has the highest entropy? Right? So think about this. We fix the mean, right? And the mean doesn't matter for the entropy anyway, so in some sense it doesn't matter. We can set the mean to 0. Fix the mean, fix the covariance, and allow all other moments to vary. And find the one that has maximum entropy. So, I mean, the moments, therefore, in some sense, constrain. You know, we said the Gaussian has 0 higher order moments, and then when we add, like when we add a skew or add a kurtosis or something, it sort of bends or constrains or changes the distribution. And so, therefore, maybe the Gaussian might actually be an interesting distribution to consider. But let's prove this. First of all, like I said, I mean, in some sense, once we shift the distribution around, if we've got a Gaussian, the mean never showed up in the entropy of the Gaussian. So we can shift it left or right or up or down, or whichever direction you want in a high-dimensional space, and you're not going to change the entropy. Because as we said last time, they're integrating over infinity over all of the range. Now, what we have, however, is that if we consider all distributions with the same first and second order moments, the Gaussian has the highest entropy. So in other words, let's say that x is a random vector, and it's not necessarily Gaussian, so this is critical. I'm not saying it's Gaussian, we're just saying it has a 0 mean and has k as the covariance matrix. Then the entropy of that distribution, whatever it is no greater than the entropy of the Gaussian. And we have equality when it is a Gaussian. When x is Gaussian, then it's equality. But if it's not Gaussian, then its entropy goes down. So Gaussian is like a maximum entropy distribution. And the proof is, you might think, how are we going to possibly prove something like this? The proof is unbelievably simple, considering how dramatic a result this is. Is this a dramatic result? It's a dramatic result. I think it's a very powerful sounding result. In fact, it is a very powerful sounding result. It's powerfully used. But considering how dramatic it is, you'll be shocked by how simple this proof is. So let's say, okay, well, G is any probability distribution. G is a distribution, and it just so happens that when I integrate with respect to G of the second moment, this is the second moment according to G, I get the covariance matrix. That's what G, or probability x having distribution G having a second moment of k means, is that when we integrate with respect to G of XX transpose, we get back k. That's what we mean. So let's say that G is any distribution that happens to have second moment. Remember, we're assuming that G has mean of 0. The random variables distributed according to G has mean of 0. And let's say that eta is another distribution which is Gaussian. and it has the same covariance matrix. So therefore, of course, according to a Gaussian, it has K as a covariance matrix, so it also has K as a second moment. So what does G and K share, or G and eta have in common? G has mean of 0, eta has mean of 0. G has second moment K, eta has second moment K. Eta has higher moments 0, G has higher moments arbitrary. That's the difference. So now if we look at log of the Gaussian, it has a quadratic form. Right? So it's xk inverse x. And this is stuff we've already seen before. We're just taking the log of the Gaussian. So we've got the Mahalanob's distance. It's 0 mean, so we don't have to subtract the mean in this part anymore. And this is the Gaussian. This is the constant that we have to take the log of. Okay. So now let's use the non-negativity of the Kohlberg-Leibniz divergence between G and eta. So here's the definition of the Kohlberg-Leibniz divergence between G and eta. So if we take G log G, we get the negative entropy of G, whatever that is, right? And G log eta. Okay. Now log eta, here's log eta up here, right? And log eta, the key thing is that we're taking, this is just this stuff here is just a constant. And we're taking the integral of g of x of this stuff. But then again, using the trace trick, we can move the k inverse over to the right of the x, and we're going to get x transpose x. Or in actuality, we're going to get, when we take the trace of that, we're going to get x transpose. So we're going to get back that same thing that we did that when we computed the entropy of the Gaussian. So therefore, what we're going to get is negative the entropy of G, whatever it is, and integral eta log eta, because when we plug into G, when we plug G into log eta, we're going to get back the same thing as when we plug into, as we plug in eta, because G and eta are the same up to second moments. And the means are 0, and the covariance matrices are K. And when we plug in log of eta, the only thing we're going to get back is something like the covariance matrix. We're just going to cancel out, we're going to get the same thing. And so that's going to give us the entropy. Even when we integrate with respect to G, we're going to get back the entropy of eta, which is the entropy of the Gaussian. And so now when we combine all the results together, we have that 0, whoops, I don't want to use that color. We've got that 0 is less than or equal to this whole quantity. So in other words, that means that the entropy of G is upper bounded by the entropy of eta, which is the entropy of the Gaussian. And finished proof. So it's a very simple result. I mean, it's a very simple proof, relatively speaking, for something that's very, very powerful. And just uses the fact that, it uses this fact, so that when we integrate XX transpose with the eta, we get back K, and also uses the trace trick, same trick that we used to get the entropy of the Gaussian.
I didn't get how it's G changes.
So when we integrate XX transpose, when we integrate XX transpose with respect to eta, or when we integrate XX transpose with respect to G, we're going to get back K. So we're going to take the integral of G of x of log of this thing, and then it's going to be the integral of this whole thing with respect to G. Right? And then when we use the trace trick, we're going to get back XX transpose. We're going to get back exactly, all that stuff is going to go away, and we're going to get back this, which is meaning we're going to get back the entropy of the Gaussian. Just because of the form of the Gaussian. Because remember, we're plugging in log of eta here. Being plugged in, this is log of eta. Eta is the Gaussian, G is not. And when we take log of eta, the only thing that's there to take the expected value of is an outer product. And by assumption, when we look at the outer product of the G, we get that K. It's remarkable, but it's true. So, okay. So then, lastly, note that the Gaussian, of course, has that entropy, and so therefore, that's true. So basically, this is in general, maximum. Gaussians are maximum entropy distributions with the same first and second moments. And in general, when you basically have a bunch of expected values of statistics, and you want essentially to find the maximum entropy distribution that has these particular expected values. So let's say the F is a statistic, and you want the expected value with respect to P to D to mu. But other than these constraints, you want the maximum entropy. The distribution is going to have this exponential form. And so a Gaussian is a member of the exponential family of distributions. And it just so happens that the statistics in this particular case correspond to the first and second moments. But in general, all maximum entropy distributions subject to the constraint that they match this set of statistics. Okay, so I'm going to pause now, and there's a couple other things I want to say, but I'm going to. I think we're going to stop right now because we want to go to the seminar. So before everybody leaves, what I want to do is.